Hello and welcome to problem set 17. Our problems today will be from the topic An Introduction to Organic Functional Groups. Before we get started, just a quick reminder that the worksheet to accompany this problem set is available online through my website. And with that said, let's get started with number 1. Which of the following functional groups contain oxygen? Circle all that apply. So I've gone ahead and written all of those up here already. So starting with A, alcohol. The alcohol functional group contains an oxygen and a hydrogen attached to some carbon chain. So you should circle A. The alcohol functional group contains an oxygen. B, aldehyde. The aldehyde functional group contains a carbonyl, and in order to be an aldehyde, on one side of the carbonyl there must be a hydrogen. So the carbonyl does contain oxygen, so you should circle B. Aldehydes have an oxygen. C, amine. An amine contains a nitrogen but not an oxygen. You should not circle C, amine. D, the amide. The amide functional group has a carbonyl, and on one side of that carbonyl there is a nitrogen. So you should circle D. The amide contains a carbonyl, and a carbonyl does have an oxygen. And finally, E, the alkyne is a carbon-carbon triple bond. So you should not circle E. The alkyne functional group does not contain an oxygen. Okay, going on then to number 2. Draw the following molecules, and we're going to go ahead and draw them in expanded, condensed, and line structures just to get lots and lots of practice. And there's an A through J. So starting with A, we have 2-pentanol. So pent is 5. The OL ending tells you it is an alcohol. The alcohol functional group is at the second position. We know because it is 2-pentanol as opposed to 1-pentanol or 3-pentanol, which would be structural isomers. So 5 carbons for our expanded structure, 1, 2, 3, 4, and 5. At the 2 position, you can go up or down. It doesn't matter because remember those single bonds rotate freely. So I'm going to go ahead and go up and put my alcohol functional group at that second position. And then I'm just going to draw lines to all of my other hydrogen just to save a little time. All right, so if you wanted to do a condensed structure for 2-pentanol, it would be a CH3 for that first carbon, followed by a CH, and again, you could go up or down here. I'm just going to go up for my alcohol functional group, followed by a CH2, CH2, and a CH3. And now it's not uncommon to see this alcohol functional group written in a condensed formula using the parentheses. So you might see something like this, especially if it's typed out. Okay, so 1, 2, 3, 4, 5, so still pent, but then this carbon, we can see that it's attached to this carbon and this hydrogen and this carbon here, and then the alcohol is off of that carbon as well. That completes the octet to that carbon. All right, finally, the fastest way to draw these once you get the hang of it line structure. So put your pencil down for 1 carbon. We want a total of 5. So 2, 3, 4, 5. And then the alcohol at the 2 position. So 1, 2. We're going to put a bond. And remember, we always have to write in those atoms that aren't carbon or hydrogen. So we're going to write in all of our functional groups in a line structure. Okay, going on to B. B is hexanoic acid. Hex is 6. The ending tells you that it is a carboxylic acid. So doing my expanded first, 1, 2, 3, 4, 5, and 6 carbons. Carboxylic acid has a carbonyl with an OH on one side. So you could have put it over here or over here, it doesn't matter, it just has to be at the end. So notice that if you put it on this side, you're just drawing the same thing I'm drawing, you're just drawing it backwards. Okay, and then I'm going to add in all my hydrogens, and I'm just going to draw lines. But if that bothers you, then make sure you're drawing in the hydrogens on yours, but just the bonds to the hydrogen to save a little bit of time. Okay, over here to the condensed. Starting out with a CH3, CH2, 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 and then we have our carbonyl and our OH. Now a carboxylic acid in the condensed form can be written as COOH. And you will probably see it that way, especially, like I said before, if it's being typed out, it's much easier to type this out. I mean, how would you type this out with this double bond here? So let's go ahead and redraw it using this method here for our condensed CH3, CH2, 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 and then it would just be COOH. And you would know that this carbon is attached to this carbon here, okay? And then it's attached to the OH, and then a double bond completes the octet for that carbonyl to this oxygen here. All right, line structure. Pencil down, that's 1 carbon, 2, 3, 4, 5, 6. Carbonyl and the OH. So just double check, 1, 2, 3, 4, 5, 6 for hex. And here's our carboxylic acid, making it hexanoic acid. All right, I think we should go ahead and erase here before we go on to part C. Okay, number 2, part C, 2-heptanone. So hept means 7, and the ONE ending tells you that you're talking about a ketone functional group. Where is it? At the 2nd position of that 7 carbon chain. So let's do expanded first. 1, 2, 3, 4, 5, 6, and 7. The ketone functional group at the 2 position, the 2nd carbon. Remember that the ketone has a carbon on each side of the carbonyl. And then I'll just go ahead and draw lines to all of my hydrogen. Okay, if you want this in condensed form, you would have a CH3 followed by the carbonyl, and then a CH2, 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 CH3. I think I got them all. 1, 2, 3, 4, 5, 6, 7. Okay. And then we can go further and condense that. Like I said before, if you're typing these out, it is more convenient to write it as CO, CH2, 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 CH3. So don't be surprised if you see it that way. So you can see that this carbon is attached to 2 carbons, okay? So in order to complete that octet, it must have a carbonyl, a double bond to this oxygen here. Now for the line structure. Put your pencil down for the first carbon. 1, 2, 3, 4, 5, 6, 7. At the 2 position, there's a carbonyl. So double bond to an oxygen. All right, D. D is propanal. That AL ending should tell you that you're talking about an aldehyde. Prop is 3 carbons. So the aldehyde with 3 carbons. So expanded first, 1, 2, 3. And I'm going to put my aldehyde on this side. An aldehyde has to be terminal because on one side of the carbonyl, there's going to be a hydrogen. That's what makes it an aldehyde. Okay, and then I'll just draw lines to all my other hydrogen. All right, for a condensed, CH3, CH2, carbonyl, and hydrogen. And the aldehyde functional group is frequently written in a condensed structure as CHO. Not COH because you don't want it to be confused for an alcohol functional group. So CHO for your aldehyde. So let's rewrite this using this form. CH3, CH2, CHO. So this tells you that this carbon is bound to this carbon here, and it's bound to a hydrogen. So then it must have a double bond to this oxygen, the carbonyl. All right, last but not least, let's do a line structure. 1, 2, 3, and that third carbon is our aldehyde, so carbonyl followed by a hydrogen. We're going to draw in our aldehyde functional group there. All right, going on to E. Pentylamine. Pent is 5 carbons and it's an amine functional group. So 1, 2, 3, 4, 5, and then the amine is NH2, and I'm going to just draw in lines to all of my hydrogen. Okay. For a condensed structure, that would be a CH3, CH2, 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 and the NH2. So 1, 2, 3, 4, 5 carbons for the pentyl and the amine functional group. We know that the nitrogen has 2 hydrogens because it's not specified that there's any substituents, any alkyl substituents off of the N position. All right, last but not least, our line structure. 1, 2, 3, 4, 5, and this bond goes to the nitrogen. So 1, 2, 3, 4, 5 carbons, and then our amine functional group. And going on to F, butanamide. So but means 4, and it's the amide functional group. So 4 carbons, 1, 2, 3, 4. One of those carbons is going to be the carbonyl of the amide functional group, and on the other side of that carbonyl, there is a nitrogen. And again, we know that there aren't any alkyl substituents off of that nitrogen. We know it's just 2 hydrogens because there's nothing indicated as being off of the N position in the name. So then let's go ahead and just draw lines to our hydrogen over here. All right, on to condensed. CH3, CH2, CH2, carbonyl, and the NH2. And finally, our line structure, 1, 2, 3, 4. That's our carbonyl. And that last bond is to the NH2. So the amide functional group here. Very common for students in an introductory chemistry class to think that this is an amine and a ketone. Don't make that mistake. When the carbonyl has a bond directly to a nitrogen, that is the amide functional group, and it's going to have different reactivity than an amine. All right, I think we can squeak G in here before we erase. G is methyl pentanoate. Okay, so that ending, hopefully you are able to realize that that is an ester functional group. So we're looking at a pent, so a 5-carbon chain that contains the carbonyl of the ester. And then on the other side of the oxygen of the ester, we're going to have a 1-carbon, a methyl substituent. So 1, 2, 3, 4, 5 for our pentanoate, carbonyl and oxygen. And on the other side of that oxygen, just a 1-carbon, a methyl group. Okay, so lines to all my hydrogen there. So condensed, this would be CH3, CH2, 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 carbonyl, oxygen, CH3. Now your ester functional group, you will frequently see in a condensed structure written as COO. Okay, so I'm going to go ahead and rewrite this using that method. CH3, CH2, 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 COOCH3. And so you would recognize that this carbon is covalently bound to a carbon and an oxygen, and therefore it has to have a double bond to that other oxygen. It has to have a carbonyl. All right, line structure, put your pencil down for 1, 2, 3, 4, 5. That 5th is the carbonyl, oxygen, and a methyl group. So just a single line there. Remember that all of these points are carbons. So 1, 2, 3, 4, 5 for the pentanoate, and then just 1 point for the methyl. Okay, let's erase and go on to H. Okay, H, acetone, a common name. So the IUPAC name for acetone is propanone, but acetone is going to be used 99% of the time, so it's a good one to know. Okay, so 3 carbons, 1, 2, 3, and it's a ketone. So a carbonyl here, and I'll just draw lines to my hydrogens. Okay, so you can see the acetyl group. Remember, that's where the name comes from. So in a condensed formula, CH3, carbonyl, CH3, and in a line structure, 1, 2, 3, carbonyl in the middle. All right, I. Acetic acid, another common name. This is the common name for IUPAC name ethanoic acid. Once again, acetic acid is going to be used 99% of the time, so you really do want to know this common name. So this is a carboxylic acid with 2 carbons. So our carbonyl and the OH. And once again, you can see that acetyl group. Here's your acetyl group. So that's where the name acetic acid comes from. In a condensed formula, CH3, carbonyl, OH. And of course, you can condense that further. We showed that before. I'll go ahead and do that as COOH. Okay. And then our line structure. 2 carbons, 1 has a carbonyl and an OH on the other side. Okay, J. Last but not least, formaldehyde, another common name. This is the common name for the IUPAC name methanal. So 1 carbon and an aldehyde. And you can see that formal group, the carbonyl with the hydrogen, often referred to as a formal group, so formaldehyde. Now in your condensed structure, it doesn't get a whole lot more condensed than this, but you can write an aldehyde, remember, as CHO. Okay, so right here, this carbon is covalently bound to this hydrogen, and therefore has a carbonyl, a double bond to the oxygen. And in your line structure, again, not really saving you any more time than this, but you would have to put a hydrogen on each side. All right, let's go ahead and erase here and go on to number 3. Okay, for number 3, we are going to circle and name the functional groups in these 2 molecules. The first is aspirin. Okay, so hopefully you recognize the carbonyl with an OH as a carboxylic acid. The carbonyl with an oxygen followed by another carbon here is an ester, and the benzene ring, or the aromatic. Okay, these are the 3 functional groups in aspirin. Over here for the amino acid serine, hopefully you recognize a carboxylic acid. An amine, and an alcohol. Now, one of the most common mistakes I see introductory students making in a problem like this is that they circle this OH and call it an alcohol, and they circle this carbonyl and call it a ketone. When the carbonyl is directly bound to the OH, it is a carboxylic acid. It has different chemistry than an alcohol. So make sure that you can recognize that as a carboxylic acid. Don't call it a ketone and an alcohol. All right, let's go on to number 4. Write a balanced equation to show the combustion of propane gas. I think we can fit that in here before erasing. So prop is 3, it's an alkane. So CH3, CH2, CH3. And I'm going to go ahead and take that all the way down to the formula C3H8. Okay. It's a combustion of a hydrocarbon, so it's combining with oxygen in a complete combustion of a hydrocarbon. The products are always the same, carbon dioxide and water. Okay. Now all that's going to change is how you balance it. So for propane, we have 3 carbons in the reactant, so we're going to put a coefficient 3 here. We have 8 hydrogens on the reactant side, so I'm going to put a coefficient 4 over here for the H2O. Now my oxygen is a total of 6 and 4, or a total of 10 in the product. To make it 10 in the reactant, I need a 5. Because 5 times 2 will give me 10. All right, let's go ahead and erase here and go on to our final problem, number 5. All right, number 5. Draw the major product that forms when one pentene undergoes the following reactions. A is hydrogenation in the presence of a palladium catalyst. So one pentene does not have a cis-trans isomer. Okay, so that's why it doesn't say cis or trans. It's going to have 1, 2, 3, 4, 5 carbons and a double bond at the 1 position, so between the first and the second carbon here. Okay, so I'm going to go ahead and draw it this way just to really emphasize that double bond, which is going to be reacting. In a hydrogenation, we're adding hydrogen across the double bond. Our catalyst is palladium, so above the arrow. Okay, so we're going to go ahead and add a hydrogen to each side of the double bond, creating the alkane pentane. So 1, 2, 3, 4, 5. And now all of the carbons are saturated with hydrogen. I'm going to go ahead and draw in the 2 that added across the double bond here, but notice that all the others are hydrogen as well. Okay. B, hydration in the presence of an acid catalyst. So again, it's for 1 pentene, and I'm drawing it this way just to emphasize the double bond and the molecular geometry and everything about that double bond. That's where the reaction is going to occur. Hydration, so we're adding H2O in the presence of an acid catalyst. So I'm going to write H plus above the arrow. Now remember that the product of hydration of an alkene is going to be an alcohol. Now there's 2 different possible alcohols that could form. The alcohol could either go here or here, giving you either 1 pentanol or 2 pentanol. Remember that the mechanism is going to follow Markovnikov's rule. That is, the hydrogen of the H2O is going to add to the side of the double bond that has the most hydrogen already, thus creating the most stable carbocation intermediate, which in this case would be a secondary carbocation intermediate. And that's how we know that our hydrogen will add to the first carbon and our alcohol will add to the second. The first carbon has 2 hydrogen. The second carbon has just this 1. The hydrogen will add to the side that has the most hydrogen already. Okay, so our final product over here is 2 pentanol. So 1, 2, 3, 4, 5. Doesn't matter if you put the alcohol down or up. I'm just going to put it down here. And I'll draw in the hydrogen that added as well. And then I'll just draw lines to all my other hydrogen, just to make it a little faster. Okay, so that will conclude our problem set number 17. I hope that you will consider tuning in to tutorial number 18. Thank you very much.